Before I ask for questions, is everybody able to open the media site links I've been sending you? Yeah? Because it's the portal login to get to it. So you click the link, it'll send you to a login page. You put your portal login and get to it. So, okay, good. Questions about homework? Anybody? Yeah? Which, 2-2 or 2-3?
2-3.
And which question was it?
B.
Part B?
Yes. Every single one of them. I got all of them right besides one with in parentheses, x minus 2 squared. What? Do you add?
No, you need to subtract first and then square.
So subtract, like if our numbers were 5, 4, 6, 3, 3, you would do 5 minus 2
Yep.
squared
Yep.
plus
Yes.
4 minus 2 squared plus.
Yes.
Okay.
Yeah, you just want to make sure that you do the parentheses first because of the way order of operations are. What was this one? It was what, 46 fifths? Yeah, so like this question right here, where we have x minus 2 squared, the sum of the quantities, x minus 2 squared. Yeah, so what you want to do here is your order of operations state that you do parentheses first. Right, so you always do parentheses, exponents, multiply, divide, and add, subtract. Good way to remember that is please excuse my dear Aunt Sally. It's a phrase for it. So we always do the parentheses first. So we do this subtraction before we apply the square. So our values are x sub 1 is 1, x sub 2 is 2, x sub 3 is 3, x sub 4 is 5, and x sub 5 is 2. Okay. So the sum from I equals 1 to 5 of x sub I minus 2 squared. And notice this notation doesn't include the sub I. That's something I like to include. So what we do here is we plug in each of these values, subtract 2, and then square it. So it becomes 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared plus 5 minus 2 squared plus 2 minus 2 squared. So you can't put this square and try and square each piece before you do the subtraction. And so then this equals, this is actually a negative 1, but when we square it, it turns into a positive value. And today when we do our measures of variability and talk about variance and standard deviation, that's something we're going to do is square the value. So we'll never get a negative value when we do our variance. All right? And it's because of this squared. You know, anytime you square a value, it's always going to return a positive number. So it's negative 1 squared plus 0 squared, right? Plus positive 1 squared, which I'm not going to include the parentheses, plus 3 squared plus 0 squared. So this equals 1 plus 0 plus 1 plus 9 plus 0. And our final answer is 11. That make a little more sense after seeing it that way? Yeah? Okay. Yeah, you want to make sure that you do the subtraction first, and then square it, and then add all the items together. And today, towards the end of class, I'll open up Excel as well, and we'll kind of look at it, as well as looking at what StatCrunch gives us. And so the answer there was 11. All right. Good question, because we're going to deal with this summation notation a lot today. Now, this is a lot different. Part C is a lot different than Part B. Here we need to square each of the x values, add them all together, and then subtract 9 from the result. You don't subtract 9 each time because there's no parentheses around x squared minus 9. So we need to sum the squared values, which is 169. It's given to us up here, and then just simply subtract 9 from it. All right? But if you did it all completely by hand, you would come up with the exact same result. Okay? All right. So let's go. Any other questions about the homework? Right. Okay, so back to our multimedia library. Let's go in and open up chapter 2. We're going to mess with and learn section 2.4 today. The title of section 2.4 is Numerical Measures of Central Tendency. And when I say central tendency, it's asking basically about where the middle of the data set is. Right? And there's multiple ways to talk about it. And we'll notice on normal curves what the relationship between the mean, median, and mode is when it's skewed to one direction or the other. Okay. So here we go. Numerical measures of central tendency. So the two sections we're going to cover today, one is numerical measures of central tendency, and the other one is measures of variability. Because if we know those two things about a data set, we can really describe a lot of things about it. If we know where the middle is and how spread out it is. That's what it's talking about. So central tendency means locating the middle of the data set. And variability means what is the spread of the data set. Is it really close together? Is it compact? Or is it really spread apart? Right, so those are the two things we'll cover today. Okay. So, when we speak of a data set, we refer either to a sample or a population. Up to this point in your homework, we've basically just been dealing with sample data sets. We haven't really been dealing with a population data set. Right? And that's just the way it's defined when you begin. If statistical inferences is our goal, which is what we really want to do, right? We want to look at this data, try to develop some patterns, look at some patterns, and then try and infer what's going to happen in the future. Right? Is it worth it if we sell gum for a nickel a piece, right, for 2 days? Is it worth it to continue to keep selling gum for a nickel a piece, right? Are we going to make money or are we going to lose money? Can we infer that it's worth our time? Or should we sell it for a dime? Right? Or maybe a dime's too expensive and people won't buy it. So that's kind of what statistic does, is kind of finds that perfect, that perfect place to be to where you can make what's called your expected value as big as possible. And a mean and an expected value are basically the same thing. Expected value is something we're going to get to when we get to probability in chapter 3 and 4. And it's really a neat thing, expected value is. Okay, so is our goal to ultimately wish to use sample numerical descriptive measures to make inferences about the corresponding measures of a population. So we'll take our sample, we'll get some numerical descriptive measures about the sample and use those to make inferences about the population. All right? As you'll see, a large number of numerical methods are available to describe quantitative data sets. Most of the methods measure one of two data characteristics. So the one for section 2.4 is central tendency. The central tendency of a set of measurements, that is, the tendency of the data to cluster or center about certain numerical values. Right? Does it tend? I know you guys have heard the phrase probably regress back to the mean. Right? You eventually become what you always were. Right? Even though one time you might be really good or really bad, eventually over the long haul, when you do the same thing over and over, you tend to go back towards the mean, towards the center. Right? That's nature. Nature pulls things towards the center. And then variability is basically the spread of the data. Another way to think about that is how inconsistent are you? Right? Some days are you really bad, some days are you really good, or most days are you basically the same? That's a way to think about variability, right? And that could be dealing with anything. Okay, in this section we concentrate just on central tendency, The most popular and best understood measure of central tendency for a quantitative data set is the arithmetic mean, or simply the mean of the data set. The mean is how your grades are calculated in a class, right? Your class average. So the mean of a set of quantitative data is the sum of all the measurements. So that's why we had to spend a whole section talking about the summation notation. So that we can do the mean, so that we can build to this point, and then finally build to variance and standard deviation in the measures of variability. So it's the sum of all measurements divided by the number of measurements contained in the data set. Sum of x over n. All right, and we'll see a formula on the next page that actually describes it. And, you know, you guys have probably heard of mean. Another word is average, you know, throughout your whole life. You know, you probably haven't seen the actual formula that creates it. You know, you've just kind of done it intuitively, come up with the mean. You know, you haven't seen an explicit formula that defines it, but that's what we're going to do here. Okay? In everyday terms, the mean is the average value of the data set and is often used to represent a typical value. Something that is going to happen more often than not. We denote the mean of a sample of measurements by x bar. So this x with a line over the top of it we pronounce as x bar. X bar is the mean of a sample. Only a sample. All right, that's what it denotes. So go ahead and write that down. X bar means the mean of a sample. And represent the formula for its calculation shown in the following box, which is on the next page. So there it is. There is the formula for a sample mean. We discussed how to apply this sum of x notation yesterday in class. So we add together all the observations and divide it by the number of observations. So in this case, there's 5, right? Notice the value on top of the summation is the same thing we're dividing by. Right? That's not coincidence. That's because we're adding up to the nth value. Whether there's 10, 20, 100, 1,000, 10,000. Okay? So using the definition of sample mean in the summation notation, we find that x bar of this data is 5.4. So if you consider these grades on papers, you know, you turn in a paper in a class, you score from 1 to 10 or 0 to 10. So here's your grades. You got a 5, a 3, an 8, a 5, and a 6. If each of the grades were weighted the same, now they have to all have the same weight, all right? And that's something we'll discuss in future chapters. But in this case, all observations have the same weight for now. Which in our class, right, our tests are weighted a little bit more than our homework. So the average is a little bit different in how we compute it. But so our x bar, our sample mean, our average grade on the test is 5.4, or on the papers we were turning in. Another way to think about the mean is if I took all of these numbers, all right, and consider these are lengths of rope, all right? So say we have a 5-foot piece of rope, we have a 3-foot piece of rope, we have an 8-foot, a 5-foot, and a 6-foot piece of rope. Basically, if I created 5 equal 5.4 lengths of rope, that's what I could create, is 5.4 foot lengths of rope. And that would basically make them all equal. So another way to think about it is, maybe this is dirt, all right? And this is 5 cubic yards of dirt, this is 3 cubic yards of dirt, this is 8 cubic yards of dirt. If I wanted to bury all that dirt in a level field, basically I need to create 5.4 cubic yard holes, and all that dirt will fit in it equally. That kind of makes sense, what happens with the mean. It basically spreads it out. So that's kind of a way to distribute all this dirt evenly. So if I had a bunch of different trucks coming in and they all had different amounts, as long as each hole was this deep, I know I can spread that dirt out evenly. Right? And that deals with water or anything else. I mean, grades. That's basically what the average is talking about. If you want to spread it all out evenly, that's kind of what the average is saying. And that's just an example of dirt. I mean, you could spread out. I mean, this could be temperature, grades, a whole plethora of examples. right? So that's what the mean is. It's the sum of all values divided by the number. Now, notice if one of these values was negative, you would just have to do a subtraction here, all right? And that would definitely change what the mean is, all right? It would significantly change what the mean is. If one of these was negative, then the mean would definitely get smaller. Does everybody see that? The average would definitely be a lot smaller. Well, not a lot smaller, it would be smaller. So look back. There is no specific rule for rounding when calculating x bar. 27 over 5 happens to be exactly 5.4, all right? But what if I had 26 over 3, right? When you start dividing stuff by 3, you get the repeating decimal forever. So there's no exact rule for rounding, because x bar is specifically defined to be the sum of all measurements divided by n. So really, if you want to be exact, you would just leave it in an improper form, all right? If it didn't round, or if it didn't equal a perfect decimal, as that one did, all right? Which is 5.4. You know, because you don't want to round off decimals, because when you keep using that calculation over and over again, you start introducing error. That's when bad stuff happens, all right, when you start using rounded values. Okay? That is a specific fraction. When x bar is used for descriptive purposes, it is often convenient to round the calculated value of x bar to the number of significant figures used for the original measurements. So that basically that says it depends on what the original measurements were. If our observations were values that had 3 decimal places in them, then I'd probably want to round my average to something that had 3 decimal places, all right? Or maybe 4 decimal places, add 1 decimal place to it. I probably wouldn't need to have 7 decimal places. Just like here, it wouldn't make sense to have 3 decimal places, all right? So it just kind of depends on the situation. When x bar is used in other calculations, however, it may be necessary to retain more significant figures. That way, you don't introduce error into your calculation. All right, that's a big deal. It makes it very different. And let me just show you an example of what that's saying. Let's consider the number pi. Anybody know what the number pi is? That's a rounded value, right? 3.14. So let's consider 3.14 to the 5th power. And then I want you to use the actual pi command to the 5th power on your calculator. Let's try that. When I have another calculator I'm going to show you today to help do this stuff. Just a little bit different method. It's still a TI. So let's just do 3.14. Does everybody know how to put the 5th power into your calculator? Use the little up pointing arrow. A Casio has a little bit different setup. But this is equal to, in your calculator, you could put 3.14. You don't necessarily need the parentheses. You put the little up pointing arrow and then a 5. That's how you do the 5th power. So 3.14 to the 5th is equal to 305.245. So I rounded that to the 3rd decimal. See how this value had 2 decimal places, so I went ahead and rounded it and added another decimal place there. What's pi to the 5th? So hit the pi command on your calculator. Pi to the 5th. Is everybody able to locate that button? Down here I have it right there. It's got the little theta symbol. And what's this equal to? 306.019, but then that 6 would round it up, so it would actually be 020, right? If I was rounding it to 3 decimal places. So this doesn't seem to be very significant. You know, you say to yourself, man, we're only off by 1. But what if this calculation was done in a computer that was designing airline parts? Right? The tolerances when you're building stuff for an airplane are very, very small. So when you start doing this calculation and you're off by just this little bit, the next time you do it, your error gets bigger and bigger and bigger and bigger. And it actually spreads out exponentially. This is kind of a small explanation of what the butterfly effect is. Small variations at the beginning can produce drastic variations at the end. Because now if you did 3.14 to the 10th, let's do it to the 10th. 3.14 to the 10th. Let me rewrite that one. And this is just to show why we don't want to round when we don't have to. All right. So 3.14 to the 10th is 93174.373. Now let's do the pi to the 10th. So would I expect it to only be off by 1, since to the 5th it was off by 1? Let's see what happens. Oh. This one's 93648.047. Now this is 500 units different. See the error that's introduced right there? Just by rounding pi to 2 decimal places. So if you only do it once, it's not that big of a deal. When you start doing it over and over again, then it really becomes a big deal. And that's what this is talking about. Okay? When X bar is used in other calculations, i.e. gets used over and over again, it may be necessary to retain more significant digits. Which means we'd probably want to take this decimal out to 10 decimal places. And it would be a lot more exact. Okay? That's what this is talking about. That's why in your homework, in 2.3, it said simplify your answer, right? Not round to the nearest decimal. It was simplify. Write it in an improper fraction. All right? Okay. So back to our gas mileage problem. All right? Remember it, the lowest one was 30.0. The highest one was 44.9, I believe, right? There wasn't one at 43. Now, I'm not making you guys go in and add all 100 of those things together by hand, all right? That's why we have computers. Thank goodness. All right? So what this is doing is it's going to give us an SAS printout, which isn't something we're going to use, but we still should be able to interpret the printout, all right? So the SAS printout below gives us a mean. The mean of our gas was 36.9940, the mean of our gas mileage. This is something we're going to talk about today, what's called the standard deviation. All right? You'll notice that the variance and standard deviation kind of look similar, in the sense that one is roughly half of the other. It's not necessarily half, it's actually the square root. The reason it looks like half is because this value is close to 2. Right? And the square root of 4 is 2, which is half. Right? That's the only one that actually happens. It even gives us our median. It gives us our maximum value. So this was the biggest value. This was the smallest value. And it gives us our n. Tells us how many observations were in it. And then we'll mess with these two in the next section. So there's our mean. The mean of the gas mileage of all 100 vehicles is 36.994. If we go back and glance at the dot plot, so I'll go ahead and just type that page in. $38. So remember this number, 36.994. So here's the data points for our miles per gallon example. There's all 100 of them. And then here's our dot plot. Now what was the mean from that SPSS? Said 36.99 or so. And look where that occurs, basically right here. You know, you can kind of tell where the mean is just by looking at our dot plot distribution. Right? You can kind of estimate where the mean is. What do you think if I kicked this thing out? Would that make my mean smaller or bigger if I kicked out that observation? Smaller, right? It'll pull my mean towards the left. So now, if I kick out that outlier, is what I'm going to call it, then this one has a significant effect on the mean. If I kicked out this one and that one, the mean would basically stay the same. They somewhat cancel each other out, right? Because 30 plus 45 is 75 divided by 2 is just about 36, right? 36, 37. So the mean of those two data points is the mean of the whole data set. So we'll see today as we talk about these measures of central tendency, these outliers, these data points that are far away from the center have an effect on what happens to the mean. Okay? All right. And we'll actually come up with a way of detecting outliers. Something that doesn't make sense. You know, the old song you used to watch, what I watched way back in the day on Sesame Street, and say, one of these things is not like the others. That's kind of what an outlier is, right? It's different than the other observations. Okay. Given this information, you can visualize a distribution of gas mileage readings centered in the vicinity of about 37 miles per gallon. Now, would that be the average miles per gallon of the parking lot right now here in Portales? Probably not, especially not with all this construction equipment, right? Because that stuff gets bad gas mileage. So we would expect the mean for that stuff to be really, really small. Or maybe I should say fuel mileage because they don't run on gas, right? An examination of the relative frequency histogram, figure 10.10, confirms that X bar does in fact fall near the center of the distribution. Which is the thing we just looked at. Okay. The sample mean, X bar, will play an important role in accomplishing our objective of making inferences about populations on the basis of information about the sample. So what that means is if these 100 cars were collected, if this sample was collected in a good manner, all right, if it was basically randomly selected from all cars on the road, then we could make a pretty valid assumption that given any car on the road, it's going to be pretty close to 37 miles per gallon, right? Every car driving has basically an average miles per gallon of 37, right? If these 100 cars were chosen in a good manner. Now you want to, if you're trying to draw inferences about a population of all cars on the road, and these cars were only parked in the, what do they call it? Like the hybrid parking lot, so to say, that's not a very characteristic sample, right? You know, here at Eastern we have some parking spots that are for fuel-efficient vehicles. You want to make sure that you're not just picking the cars that are parked in the fuel-efficient vehicle parking spots, because that's not characteristic of the population, all right? Okay, for this reason, we need to use a different symbol for the mean of a population. The mean of the set of measurements on every unit in the population. We use the Greek letter mu for the population mean, which kind of looks like a U with a tail out in front of it. When you write it down, it kind of looks like an M, especially when I write it down. There's mu right there. See how it kind of looks like an M? Kind of helps me remember. You pronounce it mu. So mu is the population mean. And X bar is the sample mean. If our sample was chosen in a good manner, we would expect these two things to be approximately equal, right? If our sample was biased, right, if I was given a task to go out and find the average miles per gallon of all the cars in Portales, and I just picked really small cars, I have biased that sample, right? That's not a characteristic sample. Basically, I would need to do a random selection. That's the best way to create an indicative sample, which is somewhat counterintuitive because, you know, how can not imposing any type of, you know, quotas or anything like that produce a good sample? But the laws of chance really do a good job, which is really a pretty amazing thing. And that's something we'll see as the summer goes on. Right? The laws of chance are the best selector. Okay. So symbols for the sample population mean, which I have written down as well. In this text, we adopt general policy of using Greek letters to represent numerical descriptive measures of the population. So we'll use Greek letters to mean population measures. All right, we'll use a sigma sign, which is a circle with kind of a tail on top to denote the population variance and standard deviation. So Greek letters pertain to population descriptive measures, and the other symbols, basically the English symbols, deal with sample descriptive measures. All right? So if you see a Greek letter, we're talking about the population. Okay? Okay. We've often used the sample mean, x bar, to estimate the population mean. Makes sense, right? I mean, that's why we take the sample. For example, the EPA mileages for the population consisting of all cars has a mean equal to some value mu. Our sample of 100 cars yielded mileages with a mean of 36.99. If, as is usually the case, we don't have access to the measurements for an entire population, which we usually don't because that costs too much money and it takes too much time, right? That's why the Gallup poll doesn't call every registered voter in the United States. And that takes years. That's why they only call 1,500, right? They only create a sample of registered voters, approximately 1,500. All right? We don't have access to the measurements for the entire population. We could use X bar as an estimator or approximator for mu. Then we need to know something about the reliability of our inference. Basically, how well was that sample chosen? That is, we need to know how accurately we might expect X bar to estimate mu. We'll do that in Chapter 7, all right? We'll find in Chapter 7 that it depends on two factors. Of course, the size of the sample. If I'm trying to make inferences about every car on the road, I want to make sure my sample isn't just 3 cars, right? The sample should be some proportion to the population up to a point, all right? And really, we'll see that a good minimum sample size for just about anything is 30. 30 is basically a good place to start, all right? Once you do something 30 times, you get a good idea of what your average is, whatever it happens to be, all right? You go out and run the 100-meter dash 30 times and find your average time, that's pretty close to what it's going to be all the way in the future, all right? Over and over again in the long run. Pardon the pun, all right? So 30 times is a good practice for that. It's like in a baseball game and a batter goes 4 for 4 in one game. Does that mean he's going to hit 1,000 for his whole career? No. That sample is too small, the size of that sample. You want a bigger sample size. And you probably hear that in TV and in movies. They'll say things like that. They'll come up with some data and they'll say, well, the size of the sample isn't big enough. We need more data. That's what they're talking about, all right? They need more data so that they can find out a little more about the population. So first thing, one of the very important factors is the size of the sample. The second important factor is how spread out is the data. All right, if I'm running a 100-meter dash and my fastest time is 14 seconds and my slowest time is 21 seconds, that's a pretty big spread, right? Now, I wouldn't expect that to be the case. Really, if you're doing that, as long as you rest enough between sprints, you would expect your spread to only be a couple seconds, right? You're basically going to run about the same time every time. Okay? So if it's really spread out, it's harder to make conclusions about the population. Right? All other factors remaining constant, the more variable the data, which means how spread out it is, the less accurate the estimate is. Okay? So that's a discussion of mu and X bar, which denotes the mean of a sample and a population. Another measure of central tendency is the median. All right? It is no coincidence that that thing in the middle of the road is called a median. All right? That's because it's exactly in the center. The definition of a median is the middle number when the measurements are arranged in ascending or descending order. What number is exactly in the center? And there are cases, and we'll see, when the median and the mean are equal, that tells us something about our data set. It tells us something about the shape of our distribution. All right? If the median's way far over to the left and the mean's way far over to the right, that's telling me that there's some outlier way out to the right that's pulling my mean that direction. Right? There's some big number that's having an influence on the mean. Whereas outliers do not have nearly the influence on the median that they do on the mean. Okay? So the median is exactly that, the number in the center. So basically, if I have 10 values, I put them in ascending order. Now, if you have an even number, there's not exactly a middle value, right? If I have 4 things, there's not a value that's in the middle. If I have an odd number of data points, then it's easy to find the middle number, right? Just like if you take your 5 fingers on your hand, the one in the middle would be the median. But if I only consider these 4 numbers, it's a lot harder to say which one's the median. The median would be the 2 middle values added together and divided by 2. It's basically the average of the 2 numbers in the middle. Okay? So calculating a sample median. Notice here they use a letter M because we're talking about the sample. Arrange the n measurements from smallest to largest. If there's an odd amount of data points, M is the number in the middle. If n is even, M is the mean of the middle 2 numbers. All right? So let's just look at a simple example here. So let's consider 1, 2, 3, 4, 5. Is there an odd or even amount of observations? Odd. So then since n is odd, right, because n equals 5 in this case, there's 5 observations, our median would be 3. That make sense? What's going on there? What about if n was 4? So let's consider these numbers. 1, 2, 3, and 4. So this is case 2, right? N is even. We have an even number of observations. So the median is the mean of the middle 2 numbers. So basically what I do is I add together 2 plus 3 and divide by 2, and I get 2.5. An important thing to remember is the mean and the median do not have to be members of the data set. 2.5 is not one of my observations here, right? It doesn't have to be. As we'll see with the third measure of central tendency, it does have to be a member of the data set, right? The mode. Okay? So let's look at another. So here's an example of an odd and an even. Let's do another one. What about if, so I'm going to leave it at 5, but I'm going to do this. So my observations are 1, 2, 2.1, 2.2, and 2.3. Oh, that's an ugly 3. What's my median here? 2.1. So now let's consider 1, 2, 2.1, and 2.2. That is an even amount of observations. So what I need to do is add together the 2 middle values and divide by 2. So it becomes 2 plus 2.1 over 2, which is 4.1 over 2, which is 2.05 would be the median in that case. All right? Now, if you do have an odd number of observations, your median will be a member of the data set. Right? It's going to be the number exactly in the middle. When you have an even number of observations, your median will not be a member of the data set. Okay? Because it's always going to be the average of the middle 2 numbers. When you have 2 numbers that are different, now that's not necessarily true because these could be the same. Right? In that case, it is a member of the data set when it's even. When you have a repeating value. Okay. So, it's not very hard to find the median when you only have 5 observations. When you have 500, it becomes a little more difficult, right? Because there's more values there. That's why we like to have computers. We denote the median of the sample by M. The median is of most value in describing large data sets. If a data set is characterized by a relative frequency histogram, Figure 2.16. There's a relative frequency. So this is a relative frequency histogram where the class sizes are very, very small. Now remember we looked at that yesterday. You know, whenever we make our rectangles really, 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 really narrow, it basically becomes a nice curve, right? Remember seeing that? Like right on page, right here on page 41. Oh, not 413. Right here. So these are all histograms. Notice when we have a very large data set and our classes get smaller and smaller, right? The width of our rectangles get infinitely small. It basically just becomes a nice curve, right? Which is what's happening in figure 2.16, a very large data set. 51. Okay. So always with the median, whatever value is the median, half of the observations are going to lie below it and half of the observations are going to lie above it. Now that's a very specific type of shape right there. That is a normal or symmetric or mound distribution. All right? That one that's appearing right there in figure 2.16. That doesn't always happen. All right, so computing the median. Here's an example I'll just kind of talk about, because we kind of already did one here. So considering the following sample of n equals 7 measurements. So that's odd, right? There's odd amount of measurements. So I need to rearrange it in ascending order, pick the one in the center. All right? So A says calculate the median M of this sample. The 7 measurements in the sample are ranked in ascending order, 2, 4, 5, 5, 6, 7, and 20. You notice 20 is not like the others, right? 20 is a lot different. But the median of this is 5. Let's go ahead and find the mean of this sample. Let's go ahead and do that. All right? What I want to do, too, is show you how to do it in your calculator. And I'm going to use a different TI right here. This is the one I was talking about that has the different columns of data. It's just a little easier to see than the TI-30 XS. So let's zoom in. So I know you guys can't see that data and I erased it. I'll go ahead and type it in. Okay. So same thing here. So I'm going to turn it on. Can you see that? Is that too dark? Let's open the iris a little more. I'm doing autofocus. All right. So here what I want to do is hit the data button to enter my data in, just like you did on this calculator, right? On this calculator, you hit the data button to enter your data. So I'm going to show you how to do it in this one. I kind of like this one because you can see all the data points right away in one screen. All right, so I'm going to enter in those 7 values. So it's 2, enter, 2, 4, 5, 5, 4, enter, 5, enter, 5, enter, 6, 7, and 20. 6, enter, 7, enter, and 20, enter. All right, so there's my data set. The same thing here, you would just enter them and keep pressing down. Right. Okay. So now I want to go second, stat. One variable, stats. I'm going to use L1. That's my list 1. I'm going to go ahead and hit enter. And calculate. So notice it gives me my N is 7. There's 7 values. And what was the median of that data set that I just put in? You guys remember? 5. It was 5. Yeah. There were 7 values. 5 was in the middle. But look at what the average is. The X bar, the mean of that data is 7. So that number 20 is pulling that mean towards it. Does everybody see what's going on there? It's skewing that data to one direction. Right? And this calculator is nice because it gives you a little more information. So there's sum of x squared, our minimum value, and then there's the median. The median's 5. This Q1 has to deal with the quartile range, which is something we'll talk about in upcoming chapters. And then there's the maximum value. It's 20. So I kind of like this calculator a little better than the other one for this stuff. Just a little easier to read, a little more user-friendly. Still cheap, not expensive at all. All right? Now you can see here, it's a lot easier. Now I really could sit and take that 100 miles per gallon ratings, and it wouldn't take me too long to punch it into the calculator. I mean, it'd take me a while, but I wouldn't have to worry about putting it in ascending order or any of that, right? And the calculator will tell me the mean, the median, the standard deviation, and all those other descriptive measures. So notice that the mean is being pulled towards that number 20, right? Towards that value that's not like the others. Okay? And now let's look at part B. Eliminate the last measurement, the 2, the last measurement in this set, not the last measurement when it's in ascending order. So when I eliminate the last measurement and then rearrange it into ascending order, here's my new data set. So the median is going to be the average of the middle 2 numbers. Now the number of measurements is even, so we average the middle 2 measurements. The median now is 5.5. So since I kicked the 2 out of this data set, is that going to make my mean bigger or smaller? It's going to make it bigger, right? Because 2 is smaller than the mean. So if I kick out a number that's smaller than the mean, now that mean is going to be pulled even closer to 20. And it's easy to do when you go back to your calculator. If I go back to my data, and what I can do here is just hit delete right there in number 2, and just slid everything else up. So now I can go back and go to second stat, one variable, calculate. My n is 6, and look what happened to the mean. It got bigger. It got pulled closer to that 20. Everybody see that? 7.8 now is the average of that data. So basically, if I took those 6 numbers, I need 6. Yeah, if I took those 6 numbers, had rope that was all that length, I need 6 equal parts of 7.8 feet, right? And they would all be equal. That's how you could distribute it equally. All right? Okay. Now, definitely you would notice if I kick the 20 out, this data is much more close together. My standard deviation is going to get a lot smaller. My average is going to get smaller. It's not going to have much influence on the median, though. Right? If I kick 20 out, the median is going to be 5. Notice how the outlier didn't have much of an effect on the median. But it would have a big effect on the average. Because if I went back to my data and kicked 20 out, the average would get a lot smaller. Right? It'd be 4 plus 5, which is 9, plus 5, which is 14, plus 6, which is 20. 27 over 5. So it'd be a little more than 5, about 5.4. So it really brought down the average. Okay? I'm going kind of slow today. All right, look back. When the sample size n is even, as in part B, exactly half of the measurements will fall below the calculated median m. However, when n is on, as in part A, the percentage of measurements that fall below m is approximately 50%. This approximation improves as n increases. Right? Yeah, because the number of values that fell below the median wasn't exactly half. Well, I need to go back here. Right? If we go back and consider part A, the median here was 5, but only 3 of the 7 measurements falls below the median. 3 out of 7 is not half, right? Not exactly. That's what that's talking about. If I get more and more observations, then it becomes closer and closer to 50%. Whereas when we have an even amount, If I put 5.5, I drew a line right here, exactly half of these observations, 3 out of 6 fall below the median, 3 out of 6 fall above the median. Okay? And we'll really see that has an influence because of discrete versus continuous stuff, and that's something we'll talk about. All right? The fact that there's a countable amount of measurements, or is it something that's not countable? All right? Like if I went out and took the temperature right now, in a second the temperature will be slightly different, right? And then a second later it'll be slightly different, right? So at any given temperature outside is a continuous measurement. That's something we'll get to. So then there's when we're dealing with continuous things, this doesn't happen, all right? This only deals with when we have a countable number of objects. Okay. In certain situations, the median may be a better measure of central tendency. Actually, in this example, the median is better because of that outlier. That outlier is having an influence on the mean. So the median actually gives you a little better example of the center of the data set, all right? Of the central tendency of the data set. You know, a good example is, say, in a class, you give 20 tests and 3 or 4 people don't show up. Those are zeros in the grade book, so that has a negative influence on the class average, right? Those zeros are really going to pull down the class average. So really, in that class, in that case, you would want to look at the median to get a better understanding of how the class did as a whole, rather than the average, because those zeros are having a negative effect on the mean. That's why whenever they talk about housing prices, it's always the median housing price. It's not the mean housing prices in an area. Because some houses are really, really expensive, right? Like here in Portales, you know, there is probably a few $1-million homes. I mean, not very many, but there's a few. But those really expensive houses have a positive effect on the average housing price, right? That's why the median is a little bit better estimator or predictor of the central tendency of what a given house, an average house, would cost. And I say average in quotes because it's not the actual average. That's why they use median housing price as opposed to mean housing price, right? In particular, the median is less sensitive and the mean is extremely large or small measurements. Note, for instance, that all but one of the measurements in part A of example 2.5 are close to 5. Right? We have this outlier of 20. 20 doesn't affect the value of the median, but it does have a drastic effect on the mean. Okay? To lie to the right of most of the measurements. That's why you have to be wary of outliers. That's why scientists are really worried about that stuff. Right? When they're studying a population, right, if they were looking at all the catfish, an average catfish weight in Ute Lake, they really got to be sensitive to if there's a few really big ones, because some catfish can get humongous. I mean, 300 or 400 pounds, where that's not very close to the average. So you really got to be careful of the outliers, right? Okay. As another example of data for which the central tendency is better described by the median than the mean, consider the household incomes of a community being studied by a sociologist. The presence of just a few households with very high incomes. Another example is a few houses that are very expensive, all right, have a drastic effect. Thus, the mean or the median will provide a more accurate picture of a typical housing price or income for the community, right? And Portales is kind of a good example of this income thing. Most people don't make a lot of money in this area, but there is a few business owners, right? Some people that own certain farms that do make a lot of money, right? So a median income is a better estimator of what a typical person would be than the mean, okay? Because if we've got one guy that lives here that makes $10 million a year, that has a drastic effect on the mean. You guys understand what I'm saying there? Okay. So here we do calculate the median for the 100 EPA mileages. That's not something we're really going to deal with. What I want to do, notice that the median, so in that data set, if I plugged it into SAS, which was in the book, right, on page, what was it, 49? Let's look at the mean and the median there. 50. Are the mean and the median close together here? I mean, they're practically the same. There's 6/1000ths of a difference. So they're practically the same. They're essentially equal, all right? So since our median and our mean are essentially equal, that tells us what the shape of our distribution is going to look like. You guys remember the shape of the dot plot? It kind of looked like a mound-shaped distribution. So whenever the median equals the mean, that explicitly tells us the shape of the distribution will be approximately normal or mound-shaped. A data set is said to be skewed if one tail of the distribution has more extreme observations than the other tail. When I say tail, I'm talking about out at the edges, all right? So there's two tails, which is kind of counterintuitive, right? Because animals only have one tail, not two tails. But in a distribution, there are two tails. So in our example from the previous page, right, the tail out to the right has a significant effect. This number 20 right here. Right, this 20 is having an effect on the right-hand tail. That tail is out a lot farther than the left-hand tail. So that's skewing the graph one direction. All right? It's basically flattening it out towards the 20. A comparison of the mean and the median gives us a general method for detecting skewness in data sets, as shown in the next box. With rightward skewed data, the right tail, the values to the right when you're looking at it of the distribution, has more extreme observations. So our example with the 4, 5 with the 20 is rightward skewed. It's skewed to the right. The tail extends out to the right. These few but large measurements pull the mean away from the median towards the right. So our average income in Portales would be skewed right. Right? Those people that make a lot more money than everybody else skew our data that direction. Okay? And then here we go. Pull the mean away from the median towards the right. That is, rightward skewness indicates that the mean is greater than the median, which is exactly what happened in that example, right? The mean was 7, the median was 5. So when the mean is greater than the median, it's skewed to the right. Conversely, which means the other way around, when it's leftward skewed, that means the mean is lower than the median, which would happen in my example of getting a few zeros on a test, right? Some people not showing up. That's going to pull the mean towards the low end. So that would be skewed to the left. Okay? These few small measurements pull the mean away from the median, but towards the left. Consequently, leftward skewness implies that the mean is smaller than the median. And then here's an example of it. So let's look at these pictures. Make it a little smaller so they'll all fit. There you go. All right, so notice this is each observation, so this is the actual values, whatever it happens to be, whether it's miles per gallon or IQ or whatever it happens to be. And then notice the y-axis is just relative frequency, right? How often does it appear relative to all the other observations? So if it's skewed to the right, notice these outliers are pulling the mean to the right. Right? Those few but very large observations are having an effect on the mean. But they're not really having an effect on the median. Here, in a symmetric distribution, they're equal. So this is our miles per gallon example. So this is the example with the 7 numbers that had the 20. It's going to be rightward skewed. This is our miles per gallon example, right, where it's symmetric. And here's an example where some people don't show up for the test. So there's a few zeros down here that's having a negative effect on the mean. Okay? So if the mean is to the left of the median, that's the way the skew is. That's how I want you to remember that. The relationship of the mean and the median. So if the mean's to the left, it's skewed left. If the mean's to the right, it's skewed right. Now you'll notice here that the peak of our graph happens to be equal to the mean and the median. The peak is the value that appears the most, right? It is the most frequent. Does everybody agree that this value is the most frequent, right? It shows up the most because it has the highest relative frequency. There is a specific name for a value that appears most often, and it is mode. So it's called a mode. The way I remember mode is the first two letters are MO. They stand for most often. The mode is the value that appears most often. A third measure of central tendency is the mode of a set of measurements. The mode is the measurement that occurs most frequently in the data set. Another way to think about it is, where is the peak of my graph? That is the mode, right? Wherever the peak is. So if I was going to take whatever data points produce that graph and randomly select one, I have the highest chance of getting the mode, right? Because it's in there the most, right? It's like the NBA lottery. The way they do that is the team with the worst record basically gets more ping pong balls in the bingo chamber. And they do it that way so teams don't lose on purpose, so they're guaranteed the first pick. So the team with the worst record is basically the mode. They're in there the most often. They have the highest chance of being picked. That doesn't mean they will get picked. This year that didn't happen. The team with the worst record didn't get the first pick. Right? I think they were actually like the fourth pick. But if you did that draft lottery over and over 1,000,000 times, the team with the worst record would get picked the most, right? In the long run, I would expect them to get picked the most. So the mode is the value that appears most often. Every data set does not necessarily have a mode, right? Now, a continuous data set does, but not a discrete one. So here we go. Let's look at this example. So does everybody have the definition of mode written down? Mode is the measurement that occurs most often or most frequent in the data set. Each of 10 taste testers rated a new brand of barbecue sauce on a 10-point scale. 1 being awful, 10 being excellent. All right? Find the mode for the following 10 ratings. What value appears the most? 9. The number 9. 8 appears twice, 7 appears twice, but 9 appears 3 times. It is possible for a data set to have more than one mode. That's something we call bimodal, trimodal, multimodal, depending on how many times something shows up. Right? A data set does not necessarily have to have a mode. If each thing only shows up once, there's no mode. Right? But something that will happen with the mode that doesn't necessarily have to happen with the mean and the median is the mode is always a member of the data set. Okay? The mode will never be a number that's not in the data set, ever. Okay? Since 9 occurs most often, 3 times, the mode of the 10 taste ratings is 9. And that's easy to do. If I put that on a dot plot, it'd be really easy to identify the mode, right? It'd be the one with the most dots. That would be the mode. Note that the data are actually qualitative in nature, e.g. awful versus excellent. The mode is particularly useful for describing qualitative data. The modal category is simply the category or class that occurs most often. So this is actually qualitative, even though we attach numbers to it. That's why you hear that rated on a scale of 1 to 10 rather than say, are you less likely, more likely, as likely, right? You know, when you fill out some surveys. That's why they like to actually attach numbers to it, so that you can find a mean and a median to that stuff. All right? Because it emphasizes data concentration, the MODA is also used with quantitative data sets to locate the region in which most of the data is concentrated. A retailer of men's clothing would be interested in the modal neck size and sleeve length of potential customers. I'll tell you what's not a mode is a size 12 shoe, because anytime I go to the store I can't find one. All right? But they always have a size 9, right? Because that's the average size that appears most often. All right? Yeah, because if you're selling men's clothing, you don't want to pick neck sizes that are huge or really small, right? You want to pick the ones that you're most likely to sell. So that's why a retailer would be concerned with that. The modal income class of the laborers in the United States is of interest to the U.S. Department of Labor. right? What income class has the most people in it? Right? And that changes all the time. Okay. Earthquake, here's some earthquake data, just a nice example here. This is a mini-tab description. Notice it gives us all the values. So here's our N. Look how many different observations there are, almost 3,000. Thank goodness we didn't have to do that by hand, right? That'd take us forever. Which is kind of amazing when you think about what the Romans and all these ancient societies, the Egyptians were able to do stuff without the use of calculators, right? And they had to do this stuff over and over again. But they didn't have nearly as many distractions as we do today, right? The mean of that data set is 2.1197. Notice the mean and the median of the magnitude is basically the same. So you would expect magnitude of earthquakes to be symmetric, right? Most of them would be right about 2, a magnitude of 2. How many people in here have been in earthquakes? A few? All right. 2, I don't even think you can feel. Can you? Yeah. Something about 3.5 is where you start feeling it. All right? And then the really bad ones, right, are when you start to get to 5, 6, 7. That's when you start having a lot of destruction. Which just happened in Nepal a few months ago. Okay. And then this is interval time for a aftershock. So notice how the average time and the median, look how different they are. The mean is pulled to the right. So the interval time to which you get an aftershock is skewed to the right. And I think that's in minutes. Right? That's what that's saying. Okay. Inter-arrival times of aftershocks. So here's my distribution of the magnitude. Histogram for magnitude of aftershocks. So most aftershocks aren't really big. Oh, that's why this number was so small, because these are magnitudes of aftershocks. This is definitely not the average of the beginning earthquake. And it depends on what part of the world you're in. So the average magnitude of an aftershock is right here, is about 2. But there are some a lot more drastic aftershocks. I mean, you start to get to almost 5 on the Richter scale, which is almost so big it's not even considered an aftershock. It's almost its own earthquake again, right? And then inter-arrival times. Both of these distributions, though, are slightly, this one's slightly skewed right. This one's definitely skewed right. And it's because, look how big this number is. 100 when compared to 2 is huge, right? So these values out here are having a significant effect on the mean. They're really pulling the mean to the right. Bless you. Everybody see what's going on there? The mode of this one is the value that appears most often, which would be right here. So, I don't know, it looks like about 10, 15. Because 25 would be here. So maybe it's about 5 or 6. All right. Okay. So the median is the value exactly in the middle. In both of these, the mean is to the right of the median. You can kind of tell just by looking at it. All right. The mode is the value that appears most often. When all 3 are equal, it's symmetric. Okay? You also notice that if we go back and look at those distributions, the picture right here, the mode, the median's always in between the mean and the mode. You guys see that? Here the mode would be to the left. Notice the median is always in between the mean and the mode. Here they're equal. Here the median is still in between the mean and the mode. Right? If you get a point where you get your median to be on one side or the other, you probably need to go back and check your calculations. Now, if you have a bimodal distribution that does this, it has 2 peaks, that's going to be a little bit different. It's just when it has one mode, all right? When it's bimodal, it's a little bit different. Okay. So that is section 2.4, measures of central tendency. You'll have a lot of practice finding means, medians for these. There's a lot of distributions like this where you can click on it and open it in StatCrunch. So those videos will be very helpful. And then you can calculate it in StatCrunch. It will save you a lot of time using it. Okay. Now with these practice problems, the data sets aren't really big, so it doesn't save you, an hour, but it'll save you a few minutes. Okay. So that talks about finding the middle of the data set. In the next section, we're going to talk about how spread out the data is. Right? How spread is our data? And that starts on page 61. Okay. We've got about 40 minutes left, about 35. Okay, measures of variability. When I say variability, I'm talking about spread. What's the variation in our data? If I'm going to randomly select values from my data, am I going to get numbers that are very close together, or am I going to get numbers that are really spread far apart? A good example of something that has a lot of variation is the incomes here in Portales. The spread of that data is going to be huge, right? There's some people that make maybe $15,000 or $16,000 a year. There's some people that make millions of dollars a year. That data is very spread out, right? Measures of central tendency provide only a partial description of quantitative data. The description is incomplete without a measure of variability. So once I know where the center is and how spread out it is, I can tell a lot about a data set. I can tell just about anything I want to know about the data set, right? Knowledge of the data set's variability, along with the knowledge of its center, can help us visualize the shape of the data as well as extreme values. All right? Suppose we want to compare response times to a stimulus for patients treated with two different drugs, A and B. The histograms for the response times in seconds for each of the two drugs are shown in these graphs. Drug A and drug B. What you notice about drug B is the data is a lot more compact, right? It's a lot closer to right here. So if you're taking the second drug, I have a pretty good guess, or I have a pretty good idea that the response time is going to be about 2.5. Look at that other data set. Look how spread out it is. You basically have the same chance of getting 1 or getting 5 because it's flat. It's almost uniform across the top. So notice the mean is almost the same in each of our 5 classes. Right? They're all basically about 0.25. You guys see that? So that data is a lot more spread out. It's a lot flatter, right? Flatter and wider. A good example of this is, say, a general liberal arts education. All right? Gen eds are basically more like this, right? You know, they kind of give you a broad knowledge, but they don't go too deep into any one subject. Right? Whereas opposed to your major is much more specific, but you go a lot deeper into that subject. Right? So really for a lot of students, their gen eds are more difficult because they're dealing with stuff that they don't have nearly as much understanding in. Or, even more of a factor, they don't have the desire to understand it as much. But when you get to stuff that you've picked, majors that you picked, it's okay to go a little bit deeper because you have an interest in it. So that's a good example of these two graphs right here. Is it flat and shallow like the kiddie pool, or is it narrow and deep like the blue hole in Santa Rosa? Right? That's kind of a way to think about it. Our first measure of variability is what's called the range. And the range is exactly what you might think if any of you are hunters or play golf or do any other type of event where you're moving objects. You want to know how far you are from something. From your point to where that object is. That's the range. The range of a quantitative data set is equal to the largest measurement minus the smallest measurement. The range from here to Clovis, if I let myself be 0, the range is what? 15 miles or so, right? Something like that, 16 miles. So the range is the distance between the biggest and the smallest measurement. A range will never be negative. A distance can never be negative. It could be 0 if every single measurement you get is the same, right? Then the biggest and the smallest are the same value, but it'll never be negative, right? Range is always positive. The range is very easy to compute and easy to understand, but it is rather insensitive measure of data variation when the sets are very large. Because if I have an outlier, my range is going to be really big when actually most of the data is packed close together, just like our example we saw in the last section. Right? When I had 2, 4, what was it? Let me write it over here. 2, 4, 5, 5, 6, 7, 20. What's the range of that data set? Right, 20 minus 2, right? So that would lead me to believe that it's pretty spread out. Right? My range is 18. But it's really not that spread out. This outlier is having a very significant effect on my range. The range is very insensitive to outliers. All right? Which is bad in this case. In the median's case that's insensitive to outliers, it's kind of good because it tells us where the center is. Right? That is because two data sets can have the same range and be vastly different with respect to data variation. Watch, here's an example of that. So here's one data set. Here's another data set. 2, 4, 6, 8, 10, 20. That one has a range of 18, but this one's a lot more spread out than this one. Right? This one actually does influence being spread more than this. Because here, if I kick that 20 out, this data is really close together. Here, if I kick that 20 out, there's still a decent spread in the data. Right? So there is a much better determining factor of finding the spread of the data than using the range. Sometimes, though, the range is all we have. All right? Sometimes we don't have all the data, and the range is all we can go by. Right? Let's see if we can find a measure of data variation that is more sensitive than the range. Consider the two samples in Table 2.5. Each has 5 measurements. We have ordered the numbers for convenience. Note that both samples have a mean of 3. You guys see that? And the median is 3. So the mean and the median are equal here. Here the mode is 3. Here there's no mode. Right, does everybody see that? But what's the range of this data set? 4. What's the range of this data set? 2. It's half the size. The spread is roughly half. Now I want you to look at this. Deviations of measurement values from X bar. How far does each of our data values vary from the average? The average is 3, right? We just found it right here. X bar is 3. So basically, how far away is 1 from 3? How far away is 2 from 3? How far away is 3 from 3? How far away is 4 from 3 and 5 from 3? There's my spread. Notice when I add all these together, what am I going to come up with? 0. That always happens. When I take each of my data points and determine the distance from the mean, if I added them all together, you always get 0. So there's something we have to do to this before we can find what's called the standard, or the variance, and then the standard deviation. You'll notice here as well, if I add all those values together, it'll be 0, right? That is always the case. When I find the deviation of each point from the mean and add them all together, so the sum of x minus x bar will always be 0. That makes sense? What's going on? The sum of x minus x bar will always be 0. So there's our spread of our data. Here's a dot plot for sample 1 and sample 2. Definitely sample 1 is more spread out. That's obvious just by looking at the graph. But we can actually attach a value to its spread. There is a measure that tells us how spread out it is. So the next step is to condense the information in these distances into a single numerical measure of variability. Averaging the deviations from x bar won't help because the negative and positive deviations cancel. That is, the sum of the deviations, and thus the average deviation, is always equal to 0. Two methods come to mind for dealing with the fact that positive and negative deviations from the mean cancel. The first is to treat all the deviations as though they were positive, i.e. find the absolute value, right? What's the distance from the mean? But we won't pursue this line of thought. Because the resulting measure of variability, the mean of the absolute values of the deviations, presents analytical difficulties beyond the scope of this text. Which means the math behind it is a little too difficult for what we're trying to teach you. Right? That's maybe your next step in statistics. If you go and take Stat 2, 313. A second method of eliminating the minus sign associated with the deviations is to square them. All squared values are positive. That's how we get rid of the negative, is we square them. The quantity we can calculate from the squared deviations provides a meaningful description of the variability of a data set and presents far fewer analytical difficulties in making inferences. To use the squared deviations calculated from a data set, we first calculate the sample variance. The sample variance for a sample of n measurements is equal to the sum of the squared deviations from the mean. So I want to know how far each data point is from the mean. Then I'm going to square that value and add them all together. All right? This looks a lot like what we were doing in your 2.3 assignment, right? And then we divide by n minus 1. The reason for dividing by n minus 1, once again, is a little beyond the scope of this class, all right? If you want to take Stat 402, we really get into why that's the case. Okay? The symbol s squared, notice how it's not a Greek symbol, right? It's a Arabic letter, our normal alphabet. So that deals with the sample variance. So the sample variance is the sum of the squared deviations divided by n minus 1. Divided by the size of the sample minus 1. So it's the distance of each point from the mean squared, added together, divided by n minus 1. There's a shortcut formula to this, because this can get pretty tedious. And here's the shortcut formula. So go ahead and write both of these down. Now, this is not something I would expect you guys to memorize. You do not need to memorize these formulas. On the exam, I will give you these formulas. You have to know how to use them. You have to be able to interpret them. So look what's going on. Isn't this the two things I talked about over and over in class yesterday, how they're different? Right? This is the sum of the squares. This is the square of the sum. That's why your calculator in your data gives you those two different values. Right? It gives you the sum of x and it gives you the sum of x squared. Notice here we're dividing by n. Here we're dividing by n minus 1. If you want to see how you can make this formula look like this formula, you can come see me in office hours and I'll show you. All right? There is a mathematical derivation for coming up with it. Those two things are equal. Even though at first glance they don't look like they would be equal. All right? So notice x bar does not appear in this formula. You guys see that? But this right here is kind of like x bar, right? Sum of x over n. The only difference is we're squaring it. All right? Now, what you can kind of see if you kind of split this up and kind of apply the square into it, there's the sum of our x sub I squared. It's not exactly, it's just similar. All right? That's not how it doesn't just, you apply that square and you can't do it that way. That's not mathematically sound. But this does kind of look like the average, right? The sum of all the values divided by n. But we have to square the numerator first before we divide by n. Okay? With this formula, you want to make sure that you simplify the entire numerator before you divide by n minus 1. Something else I want to emphasize is this n minus 1 needs to be in parentheses. Okay? Let's say, for example, let me show you a bad thing that would happen if you punched it into your calculator this way. Let's just say I did all the computation in the numerator. N is equal to 8. Let's just say I've done all the computation in the numerator. So s squared equals, let's just say, for example, this is, I don't know, 100 minus 1,000 over 8 divided by n minus 1, which is 7. Right? So I'm going to write it as 8 minus 1. Be careful that you do not write this. Here, let me erase that and just put a value up here. Let's just say it's 27.7. But that's not exactly what it was. I'm just pulling that out of my head. Be careful that you do not write it this way. S squared is not equal to 27.7 divided by 8 minus 1. Why would that give you a wrong answer?
Subtract by 27.7 by 8.
Right, because it's going to do 27.7 divided by 8 and then subtract 1 from the result. So you have to make sure that that denominator is in parentheses when you put it in your calculator. Does that make sense what's going on right there? And that's a normal error I see. So the best thing to do would just be to come up with 8 minus 1 and just write 7 right here. And then you don't have to worry about it. Okay? Okay. Referring to the two samples in table 2.5, you can calculate the variance for sample 1 as follows. So this is from the previous page. Sample 1 and sample 2. So remember, sample 1 was, it had 1, 2, 3, 4, 5 were the observations. So here our variance would be 1 minus 3. Remember, this value was negative 2, but when you square it, it becomes positive 4. So 4 plus 1 plus 0 plus 1 plus 4, because 5 minus 3 is 2, 2 squared is 4. And then over 5 minus 1, because there were 5 observations. The fact that this number's 5 and that number's 5 is just coincidence, right? That's how the data set was built. So when I do all this, when I add together the numerator, and I add 5 plus 5, which is 10 over 4, I get 2.5. The variance of this data is 2.5. But we don't really deal with the variance. We deal with what's called the standard deviation. The standard deviation is simply the square root of the variance. So the standard deviation is s when the variance is s squared. So all you do is just square root 2.5. Do that in your calculator, right? So the variance of this data set would be the square root of 2.5. Which is, what is the square root of 2.5? Everybody know how to do square roots on their calculator? 1.58. The sample standard deviation, S, is defined as the positive square root of the sample variance, S squared. And we say the positive square root because it is possible for the variance to be a negative value. Because of this subtraction right here. Okay? Standard deviation never will be negative, though. Because it is possible that this piece is bigger than that piece, so that's going to lead it to be a negative value. That's why it has to say the positive square root. There we go. So the population variance denoted by the symbol sigma squared. So that's population because it's a Greek value. Greek letters deal with population. Arabic letters deal with the sample. Right? Is the average of the squared deviations from the mean mu of the measurements on all units in the population, and sigma is the square root of the variance. So here they are. So sample variance is S squared. S is the sample standard deviation. We deal with the standard deviation a lot more than the variance. You just have to be able to find the variance to find the standard deviation. Okay? And population variance is sigma squared. Population standard deviation is sigma. This happens to be the lowercase symbol of our summation sign, which doesn't really, most of the Greek letters, the capital and the lowercase kind of look similar. Sigma is not one of those. All right. Now let's do an example. Notice that, unlike the variance, the standard deviation is expressed in the original units of measurement. For example, if the original measurements are in dollars, the variance is expressed in peculiar units dollars squared, but the standard deviation is expressed in dollars. That's why we like using the standard deviation better, all right? So for our miles per gallon example, the standard deviation would be the standard deviation of the miles per gallon, not the miles per gallon squared, because that really doesn't make much sense, all right? You may wonder why we use the divisor n minus 1 instead of n when calculating the sample variance. Wouldn't using m seem more logical? The trouble is using n tends to produce an underestimate of the population variance. So we use n minus 1 in the denominator to provide the appropriate correction for this tendency. And then see that little star? That's explained down at the bottom of the page. Right? It's because of an unbiased estimator, which isn't something we're that concerned with. All right? Just know that that's what we do. Since sample statistics such as S squared are used primarily to estimate population parameters such as sigma squared, n minus 1 is preferred to n in defining the sample variance. So let's do this. So let's calculate the variance and standard deviation of the following sample. Okay? So let's do it by hand, and then I'll show you how to do it in your calculator. And I'm going to do it using both formulas. Okay? So first I'm going to do it using the long formula. So S squared is equal to the sum of the x sub i's minus x bar squared over n minus 1. So what's our x bar for this set? What's our mean? 15 over 5, which is 3, right? It's x bar is 3. So S squared is going to equal 2 minus 3 squared plus 3 minus 3 squared 3 times, right? Which is just 0 3 times. All over n minus 1, which is 5 minus 1.
Where's the 3 coming from?
That's the average. And that was given to us, remember, on the first page of the section? Right here on page 61. So this is the second sample. Sample 2 is the one we're finding the standard deviation for. And remember, we found the x bar before, and it was 3. Right? So what we're doing right now is finding the variance and the standard deviation of this set of data. Now, you guys told me that the variance for this set, or the standard deviation, was 1.58, right? The square root of 2.5. And you guys agree that this data set is less spread than that data set? Sample 2 has less spread? Yeah? So I would expect this standard deviation to be a lot smaller than 1.58. So let's keep going. All right. So S squared is equal to 2 minus 3 is 1. 1 squared is 1, right? 1 plus 0 plus 0 plus 0 plus 1 over 4, which equals 2 over 4, which is 1/2, or 0.5. So S is equal to the square root of 0.5. Is the square root of 0.5 going to be bigger or smaller than 0.5? You would think, because most of the time when you square root something, it gets smaller, but not for values between 0 and 1. Let's go ahead and punch it in your calculator. Second square root, you go exit. Okay, second square root 0.5, and the answer is 0.71. So the standard deviation of that data set is 0.71. What was it for sample 1? Remember, it was 1.58? So this standard deviation is basically half, right? It's half is spread out as sample 1. So there's the variance and standard deviation of that data set. And then the book shows you how to do it using the shortcut formula. So here's the shortcut formula. Let's take a look at it. Kind of running out of time, and I want to show you how to do it in your calculator. This is why we like the shortcut formula better, because we don't have to go in and perform all of these subtractions. You know, imagine if we had to do this for 100 observations, right? That would take a lot of time. It's a lot easier to do it this way with 100 observations, especially because your calculator, remember the values it gave you? It gives you sum of x and sum of x squared, right, in your calculator. So the sum of all the x's was 15. The sum of the squared values is 47. So look, 47 goes right here. 15 is sum of x, so it goes right there. 47 minus 15 squared over 5 divided by 5 minus 1. So let's verify that this is what we get. So let's do this in the calculator. And actually, you can type this line directly in, because your calculator will do order of operations. So you could do 47 minus 15 squared divided by 5. And you get 2. And then divided by 4, and you get 0.5. And then the square root of 0.5 is 0.71. Okay? Okay, so I'm going to punch this into my calculator and come up with these values again. All right? And I'll do it in both calculators. Let's go document camera. So I'm going to go to my data command in both calculators. So I'm going to do this one first. So it was 2, enter, 3, enter, 3, enter, 3, enter, and 4, enter. And I'm going to delete out everything else. So there's my data set. Over here I'm going to go 2, 3, and I'm going to do frequency on 3 to be 3, and then 4. Then I'm going to go down here and I'm just going to start pressing delete to get rid of all those. Now I want X4 to be blank. So now I have my data punched in both cases. So I'm going to go second stat, one variable. Stat var. Then here I'm going to go second stat. So notice in both cases it's 5, right? My n value is 5. This one already tells me X bar. My average was 3. If I go over here and press to the right, there it is. My average is 3. So with this sigma x is a weighted variance, right? That's a weighted standard deviation, so just ignore that one. The standard deviation is the S of x. So notice I get the exact same standard deviation. Rounded to 2 decimal places, it's 0.71. All right? And this calculator, if I go over to the right, notice it gives me my sum of x, which was 15, and the sum of x squared, which was what? You guys remember? 47. So when I click to the right, it should be 47, right? And lo and behold, it is. All right? Same thing with this calculator. I go down. Sum of x was 15. Sum of x squared is 47. This one tells me a minimum value. There's my median, maximum value. It doesn't give me the range, but it gives me my minimum and my maximum. So it's easy to find the range. So in your calculators, we take S of x, not sigma x. All right? So now this is nice because you can put in really big data sets now and not really have to worry about it. Now, I will say, do not use this calculator as a crutch. You have to be able to do this stuff by hand, right? On your test, I'll ask you a question, maybe give you 6 or 7 data points, and you have to be able to find your standard deviation by hand. Either using the long formula or using the shortcut formula. Now, you are welcome to use your calculator to check your answer, but I need to see the operations written out. After the first test, once we start getting a little bit further, then you can use the calculator for this stuff, right? But on the first test, I will be testing you on being able to find the standard deviation by hand. Okay? Does that make sense what I'm talking about? So use this as a tool, not as a crutch. Like most things in college, right? There's a lot of ways. I mean, you could use a lot of things as crutches, but in the long run, it doesn't do you any good, right? Use it as a tool. Okay. That is basically about it. Let's look at the standard deviation and variance and verify it for our miles per gallon formula. So here's the SAS readout for our cars. So I could say this data is pretty close together because the standard deviation is pretty small when compared to the mean. But we'll actually come up with a systematic way to say if our data is close together or far apart. Okay? We'll actually be able to do that. Is the square root of this number equal to that? Try it. Put it in your calculator. So let's go second. Clear second. Square root. 5.8462263. Square root is 2.4178971. So what this means is the average miles per gallon for those 100 cars is 36.994 miles per gallon with a standard deviation of 2.4 miles per gallon. So that means if I go 2.4 miles per gallon above 36.9 and 2.4 miles per gallon below 36.9, I'm going to get a lot of the data in that interval. Exactly how much of the data, we'll find out, right? We'll see. And there's actually something called the empirical rule that tells us how much data falls within that interval. How much falls within 1 standard deviation, within 2 standard deviations, and within 3 standard deviations. All right, so that's where we're going with this. And then I can create an interval and have confidence that most of my data will fall within that interval. That's where the word confidence interval comes from. Okay? So, due tonight is 2 and 2, 3, right? Is due by midnight tonight? Yeah, right here. So today is the 4th. So due by 2, 2, and 2, 3, due by midnight tonight are those 2 sections. So the 2 we covered today, look, you have until Monday to turn them in. All right? I know some of you have other summer classes you're taking, other obligations. That's why I give you some time. And I also have, so on Monday you can come into class. If you have questions, you can ask me. All right? Now this doesn't mean wait till 11:30 on Monday night to do this homework. Right? I would encourage you to do it as soon as possible. Because then if you have a question, you can email me and I'll get back to you. All right? So on Monday, we're going to cover 2.6 and 2.7. All right? That's the next 2 sections. So we only have 4 more before the exam. And notice the quiz isn't showing up. You need to always click this Show All button, and then View All on one page, which is over here. And then the quiz shows up. All right? And that's due a week from today at 9 a.m. That's when we're going to take our exam. Okay? Questions about this? Where's my sign-in sheet at? Back there? Okay, did everybody sign it? All right. All right, thank you, everybody. Have a wonderful weekend. We'll see you on Monday. Email me if you have questions. Oh, it's because you're not in the step.
Oh.
Yeah, you need a second step, one variable. Now it's expecting you to put it.
Okay, okay.
I saw the multi-camp packs, so I kind of figured. Which year? Army, 25 year.
What do you think, Crystal?
I'm going to get through this class. It helps that I took 106
Oh, yeah, definitely.
last semester.
I mean, we designed that class to be something to lead into this class. We specifically picked things to cover in there that students had trouble with in this class. You know, so
I still have my notes.
Mary Beth was your instructor.
Yes, and you know she had printed out notes.
Yeah.
We never had a book at all.
Right. Yeah, lecture guide. Yeah.
And
Well, because the book we used for that class was actually called College Mathematics, and we only used like 4 chapters out of that book.
really,
Yeah.
see, I had taken college math back in '99. I started, I think.
Yeah.
Times, and I failed out of it.
Oh, dang it.
I could not get through it. So when I came back, I was like, I'm getting math out of the way.
Right.
It's the first thing I'm getting out of the way.
Like, what's your average and standard deviation for drink price?
For drink price, I'm going to call it $5.
Would
Oh,
No, I'm saying all drinks from your lowest to your most expensive.
okay.
Because then you have to consider your shots.